now. So that should have a, as usual, maybe a 5 to 7 second of delay or lag time. All right. So we're gonna do some C coding today, as we do a base conversion of not just your usual base conversion, but for double precision floating point numbers. So that's going to be the focus of tonight, is how do we do that? And here we have the floating point number representation module. There we go. And I'm thinking maybe I need to change some of the, it's a minor change, when we get to it, we'll get to it. So there we go. And we got 2 minutes and a half to go. If anyone has any questions to ask, now is a good time as usual. No questions. Okay. All right. So as you might have noticed, things are getting a little bit more complicated. Floating point number representation is the very last topic of how we represent values, and then we're going to move on to memory devices and what we call the von Neumann architecture. And then after that, we'll get started with actual assembly language programming, which some of you have been waiting for a few weeks already. So we'll see, when we get to that point. You may notice that it's not the kind of programming that you have been expecting. But today we're going to talk about regular C programming. So anyone with a prerequisite of CISP310 should not feel foreign to the concepts that we're going to be talking about today. Or at least I would hope so. Alright, we got 1 more minute to go. And I'm going to get to the portion that I need to get to. There's never enough time in this class to really teach everything that I have prepared. I wish there was enough time, so we're going to have to skim through some of the material, because otherwise we won't have enough time to actually get all the stuff into this class. Alright, we got 20 more seconds and I'm not seeing any questions. Alright, we got about 7 people on YouTube, and I'm gonna guesstimate maybe 20-ish, on Discord. Yeah, so where's the rest? And the whole idea of having a 5:30 starting time is to accommodate people who have to work during the day. So that's why I don't take roll like really early in the class, is to get people, give people some leeway, some time to, just in case there's traffic or something that delays when they get home. All right, well, it is time. In fact, we are 40-something seconds past 5:30. So I'm going to get started here. What you're seeing here is the regular expression of, one way to represent a base 10 scientific notation. So I'm just going to get through this really quickly because, I'm not going to test you guys on whether you understand regular expression or not. All right, so the full explanation is actually in the notes. I mean, it's fully explained here. So for those of you who have been trying to learn regular expression because of some of your other context, you can actually learn regular expressions just by reading the explanation, or at least some portion of regular expression here. If you have never heard of regular expression, um, yes, I can tell you that the exam will be graded when it's graded, because it's gonna take some time, because all of those are open-ended questions, and I'm gonna follow the reasoning, of whatever people wrote down, and see if see if everything is okay. If I spot problems, I'm gonna have to make a mark, and if not, I'm gonna they're gonna get the credit. So it's gonna take some time to go through, because I do go through every single line of stuff that people write as a part of the answers. So I'm not just gonna take a glance at it and go like, nah, this is not the answer, and then just give a big O0 over there. I wish I could do that, but that would not be fair. So that's why it's going to be a little bit time consuming. Now, if you want me to give you the solution, that I can do. Okay, that's actually, well, okay, my script is it can automatically generate the answers to the first three questions, but I don't have the code yet to generate the answers for the last three questions. The one that converts from base 6 the one that performs addition in base 6. So I can explain that a little bit later today if I get time at the end of today's class, but I do want to go over enough stuff so that you can get to, the lab started. The lab is not due tonight, okay? So for those of you who want to ask me, so do we have a lab tonight? The answer is yes, but it is not due at 9:50 p.m. That's because this one has a little bit of coding in it, and I don't want to give you guys too much of a constraint when it does involve a little bit of coding, because I really want you guys to really spend the time to think about how to get this done, and then write the code, okay, and then debug the code. So I'm giving you until next Tuesday at 5:30 to turn in. This is not an invitation to procrastination, okay? Just given you have almost an entire week doesn't mean, at all that you should procrastinate. In fact, as we get closer to next Tuesday, I will kind of sticking to my response time, policy, because I hope you guys still remember the response time policy. It is within 24 hours. Okay, so that means I can see a text coming in Discord and not reply within 24 hours, or until it's my office hour. Um, I'm probably not going to do strictly that, but I'm going to intend. I'm intending not to look at my Discord unless, okay, I am, in my office hour, which is to encourage people to get this done earlier, okay? Because if you get this done earlier, that wouldn't be a problem, right? If you get this done before Thursday or shortly after Thursday, then the entire weekend is yours. Nothing to worry about, it's all your time. All right, well, but I found out that no matter how much I preach, it doesn't matter. Some people are just going to wait until the last moment. Not going to be able to do much about that. Okay, so getting back to on topic here. So this is basically how we express a base 10 scientific notation. When you see square brackets, that means whatever is enclosed is a group of characters. Choose one of those characters. That's basically what it means. So when you see this construct here, that means out of the two characters, plus and minus, we can choose one of them. And then we see the backslash equal to. Backslash equal to means whatever is before, we can have 0 or 1 occurrence of that. So that means when you combine these two, that means the sign is optional, and the sign can either be a plus or a minus, but it is optional. Are we doing okay so far with this? Maybe, maybe not. Okay. And then what is next is going to be a character, and from 1 to 9. So we are not referring to the value of 1 to 9, we are referring to the character from 1 to 9, and it is a single character. So this is not saying 9 characters, this is saying one single character, but that can be chosen from the character 1 all the way up to the character 9. And then after that we have a backslash open parenthesis, which is matched by a backslash close parenthesis over here. So parentheses are used for grouping purposes. In other words, they are sort of equivalent to braces, the curly braces in C++ programming. It is here so that we can form structures of blocks. So let's take a look at what is in this block here. The first thing in the block is backslash dot. That means just literally dot. And that's because dot by itself, without the backslash, which is an escape character before that, means to match any character. So this way, we are saying, okay, match exactly just the dot character. Followed by backslash d. Backslash d is one of the 10 digits from 0 to 9. And this is from 1 to 9. That's why I cannot use backslash d here, because I intend this first digit to exclude 0 itself. But here we can have 0, 1, all the way up to 9, and a shorthand to designate all the base 10 digits is backslash d. And then a single asterisk right after that means whatever is before can have any number of occurrences starting with 0. So that means it is referring to the base 10 digit that can go from 0 to 9, and we can have any number of those digits, including 0. And that means this entire group is just saying, okay, let's start with a dot and then followed by any number of base 10 digits. That's what this entire group is trying to specify. And then this entire group is followed by a backslash equal to, which we have already talked about. This means it is optional. We can have 0 or 1 occurrence of whatever is before the backslash equal to. So this time it is applied to the entire group here. So that means the dot blah 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 is entirely optional. You can have just a single digit with no fractional part, and that is okay with according to this syntax specification. And then after that, we have another group, backslash open parenthesis here, and then backslash close parenthesis over here. So now we have another group. Inside the group, we start with the lowercase letter e, and e has no special meaning in this case. It really just literally means the character e, okay, which we already have talked about, right? The lowercase e is the separator between the coefficient and the power of 10 in a base 10 scientific notation. And this part here we have seen already. Okay, so the sign of the exponent of 10 is also optional. Obviously, if it is missing entirely, it is implicitly a positive exponent, but it can be missing entirely. And then after that, we have backslash d again, which means another base 10 digit from 0 to 9 in this case. And then this time we are not followed by a backslash equal to or a asterisk. This one is backslash plus, which means at least 1. So give me at least 1 base 10 digit, but we can have more. So this entire group is basically specifying the fact that we can have a base 10 exponent specification. It has to start with a lowercase e, it has an optional sign plus or minus, and then you specify the exponent of 10 using at least 1 base 10 digits. And that's it, right? And this entire thing is also optional because this entire thing is followed by backslash equal to. So that's kind of one way to specify a base 10 scientific notation in which you have a true mantissa, because the coefficient, which is specified by this portion here, has to start with 1 can only go up to 9 point blah 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 9.999999. As a result, this is a true mantissa. It is normalized. Alright, so I'm going to pause here and see if there are any questions. I can hear crickets. Well, that's sort of what I expected, because I already said, oh, I cannot test you on this, right? So when I think most of the time when I preface my lecture or a portion of a lecture and say that, well, there's nothing I can test here in an exam. Many people do not need to pay attention. However, for those of you who did pay attention, because you have encountered a situation where regular expressions seem to be useful, this is one way to kind of explain it. Yep, look at that. What is the main intention of creating regular expression? That is a very good question. It's for validation of text, anything that involves text. Regular expression is used a lot in web scripting, especially when you have user input to validate. Regular expression is also very useful for parsing. Now, regular expression has its limitations. It cannot handle certain types of languages like C and C++. Now, that's way too much for regular expression to handle because it is structured, it has nesting, and has basically an infinite amount of nesting that is possible. So regular expression cannot handle nesting all that well. Now, if it's a fixed number of nesting levels, it can do it, but if it is an undetermined number of levels of nesting, it cannot deal with it. It is a very interesting introduction to one of the topics that you are going to encounter as an upper division class in a four-year university. Most of you probably will have to take a class in what we call automata or computational theory. So that traces all the way back to Alan Turing, when he was modeling computer behavior of computers using state machines. And so there's a one-to-one correspondence between the language that you can specify versus the classification of machine according to Turing's classifications. So this is a good kind of introduction to all that stuff. Maybe at some point you guys would go like, I vaguely remember Tech talked about something like that, which probably is gonna happen. All right, so let's see. Backslash is the escape. So backslash is just escape, okay? Because when a certain character has a special meaning, then okay, let's just say that you really want to match the asterisk character, but because the asterisk character by itself means any number of whatever is previous to it. So you cannot just say asterisk because it will be misunderstood as any number of whatever is before that. So now you need a backslash to basically say no, I don't mean this as a quantifier. I really mean this literally as the asterisk character. So that's basically what the backslash is for when you specify something like this in regular expression. Alright, so I'm going to skip all of this stuff here. And this is just an instance of a base 10 scientific notation. And it is negative 2.67 e negative 6. And it is parsed as follows, and so on and so forth. Now, why is this important? Well, that's because I am going to give you a program that already contains the parsing of a base 10 scientific notation. And let's go ahead and give this a try. Okay, so I'm going to get into the lab. So I'm going to release, well, not to release, but I'm going to make the lab visible, which means it's quote unquote released. There's no passcode to this particular lab. All right, so let's go to it's called negative exponent. There we go. Alright, so you guys can access it too, because it's already released or published. So go ahead and take a look at it. And what I'll do is I am going to so don't do anything, because if you are trying to do stuff, when I'm trying to explain something, you're not going to be able to hear me explaining certain things, right? So don't do anything while I'm explaining it, because everything is being recorded. I'm pretty sure, because I'm looking at YouTube. It's ongoing, so I know it's being recorded. Alright, so in this case you have one single source file to deal with, and it is here. You can click it in Canvas. So you can click it in Canvas and it will render it in a certain way. Now don't do that, okay? Because the best way to do it is not to click on it. The best way to do it is to click on the little download symbol here, which should trigger your browser to either open it automatically, if you already have a type of application associated with .c, or it will ask you whether you want to save it or not. And in this case, I'm going to save it. And into my temp folder, it's monolith-1. So I'm going to rename it as monolith.c, just so they don't have to type that -1. And there we go. Okay, so this is just a file. And I'm going to use online GDB, and you should be using whatever environment you feel comfortable with. Okay, so online GDB is not the only environment in which you can do this homework assignment. If you already have a good C compiler environment that you have set up already and you have used it in CISP360, keep using it. Okay, there's no reason that you have to use online GDB. On the other hand, if you say, but I don't really have access to a C compiler because I have been using a lab machine or some other online resources, well, this is actually a pretty good resource. Let me show you what it looks like using onlinegdb.com. I'm going to open this as a new tab. And this is it. It's only relying on having a browser. So you can have a Chromebook and be able to do this. All right, so a few things. First thing is you might want to sign in and create an account. It doesn't really matter what email address you use, to sign in. You can just go get a new Gmail account just for this purpose if you don't want, potentially getting spammed because of this user interface. Okay, so it's your choice. Okay. I don't think I have ever gotten anything, spamming, any spam from this site. Yeah, you can use Replit too. I have not used Replit for a while. I'm not really sure whether Replit can do the debugging that I am going to do here. So again, and you can kind of evaluate, whether you can do this in Replit. All right. So first thing first, I'm going to have to open up the file that I just downloaded so I can copy and paste it into here. And let's see. Yeah, so you can use Replit. I mean, the only concern that I have is whether you can debug your program effectively using Replit or not. Because last time I tried with Replit using with a C++ program, it did not give me a debugging environment where I can execute commands like I can in GDB. But that may be just me, okay? Maybe I did not dig deep enough to find out how to do debugging in Replit. So you guys are welcome to use any resource that you want. The bottom line is when you turn in the program, it has to be able to work in online GDB. So that's kind of the bottom line. All right, so let me get that program into here first. So let's see, it's xclip, that's cell clip. I'm executing a command on the side here, and it's called what? Monolith. Okay, monolith.c. And now I can get back here. Just do a select all and paste, and now we have the entire program in. So the regular expression stuff, the part that specifies the syntax of a base 10 scientific notation that is normalized, having a normalized mantissa, is done by parse already. So you don't have to do a single thing to parse it. Okay, it's all done for you. On the other hand, for those of you who are curious of how this is done, you can actually look into the logic of this portion of the program. It's definitely optional. But for those of you who like to read the source code of other people, this is, you can do it. All right, so what are you going to do, right? When you get this code, so the first thing you want to do is to find a subroutine called, let me see, it's the only empty subroutine here. It's called E10 to exp2, and let me find the body of that thing because it should be empty and not have anything in it. That's parse right there. There we go. So this is the subroutine that is empty, and your job is to complete this particular subroutine here. Alright, so I'm not going to do your homework, obviously, but I can show you by the time you get into the subroutine what you can expect to see and how to get here. So once again, you might want to just kind of jot down the time, which is 5:51:04:05-ish, because you probably will need to come back to this point here to kind of learn how to navigate around in online GDB. So yeah, it could use a header file. The problem is online GDB doesn't deal with multiple files, so that's why we have a monolithic program here. Yeah, that's one of the limitations of online GDB. But yeah, I know Rapid does too. Does handle header files or multiple source file, in the project. But there's one thing online GDB does really well. I'm gonna show it to you. So the first thing you need to do is to select your language. Now this program is a plain C program. You can just specify C and it's going to work. I believe you can also specify C++ because C++ is really a superset, which means it includes everything that C has and then plus some extra stuff. There's actually a little bit of stuff where it is that C++ differs from C, which means you cannot just take a C program and certain things may not work. But this program should work in C or C++. But I'm just going to specify C over here, and then I'm going to click Debug. Okay, so it will compile the program, and it's going to give you a command line interface, which is GDB. Now GDB stands for GNU Debugger. That's it. Okay, that's GDB. And GDB it looks archaic, it looks like, something from the 60s, and why are we doing something that has a command line interface? It's actually very flexible, and it's scriptable as well. And that's the one thing that I really like about GDB is it's scriptable. But that's a, topic for another day. So right now, I just want to run the program. So let's just say that we want to test a specific base 10 scientific notation, which is 1.234E45. Okay, 56. There we go. 56. There we go. So the dash n is required because that's how the program is expecting. So dash n and then the space and then 1.234E56. Those are arguments that we are passing through the command line to a program. And these are being done using the argc, argument count, and argv, which is argument value, of every single C program. In your CISP360 class, I really doubt that this concept was discussed in your class, but it's okay if it was not. Okay, it's no big deal because everything is handled by the program up to this point. But the key point here is when you test your program with a specific value, you have to specify -n, which means the number I'm testing is as follows, and then give it the actual number that you're going to test your code with. Alright, so we got several people typing in the text channel, so I'm going to pause here and see what questions people have to ask. I believe so, Omer. I think struct is supposed to be included, no matter which college you take CISP 360 from. But then, I understand sometimes instructors run out of time. So, but it should be taught in CISP 360. If not, you can find lots of online resources that will teach you how to use a struct. And in fact, this program also shows you how to use a struct. So you just have to kind of look through the code here and find out, how a struct is used. All right. Okay, so I can explain a little bit. Okay, that's not a whole lot to it. Okay. Yep. Structs are actually like class. Okay, a struct is like a class where all the members are by default public. And in C, a struct cannot contain a method, so it cannot contain a function. It can only contain like specific types of values. So that's it for the most part. That's what a struct is. It's really just a class, except it's kind of limited in terms of what it can contain. it's not a collection of variables, it's a collection of what we call members. So let me just run this program, and then it'll be clear what I mean by that. All right. And here is the breakpoint. So the breakpoint is on line 126, which means when the program gets to that point, it's going to pause so that I will get a chance to examine, my local variables and whatnot. So I'm going to press the Enter key, and right here it stops. So when it stops, the only local variable or the only local name that I can refer to is pn, which is a pointer to a struct float 102. 102 is really 10 and 2, okay? Because this floating point number has both the base 10 and the base 2 component. And let's go ahead and examine what that thing looks like, okay? So you can say print pn, it's not going to be very helpful, because all that is going to do is to tell you that is an address, which is this part here. It's not important to us in this class, but it will also tell you the type of the pointer. It is a pointer to a struct float 102. Not exactly helpful. So what is more helpful is to say print asterisk pn. Asterisk is dereference. In other words, you're given a pointer, and when you use asterisk, it will tell you what it is pointing to, the content that is being pointed to. So there we go. So now we see that Pn is pointing to a structure that has several members. One member is called sign, and it is 0. It kind of makes sense, right? Because the sign bit is supposed to be a 1 only for values that are negative. And the value that I specified is not negative, so having a sign of 0 makes sense. This is the coefficient, and go like, oh, but how come the coefficient is 1234 instead of 1.234? That's because in this homework assignment, I have a restriction. You cannot use float, double, or anything from math.h. You can only use integer variables, integer math, integer arithmetics, but you cannot use floating point numbers. Okay, so that's one really big limitation, because you cannot use log, you cannot use exponent, you cannot use anything from math.h. Yep. So I'm gonna tell you guys how to do it. Okay, so don't worry. There's a really efficient way of doing conversion without using those double and float stuff. So this is E10, which is the exponent of 10, and this is E2, which is the exponent of 2. So what are these names doing here? What exactly is the value? So let me go back to the lab description here. So the value being represented is coefficient times 2 to the power of E2 times 10 to the power of E10. That is the value that is being represented. So have I changed the value being represented, going from the string representation given to the program versus the components of whatever Pn is pointing to? So we'll get back to this after I tell you what the road taking word is for tonight. Alright, so let me make a new tab because I don't want to lose track of the lab page. So we are looking for 2022 March 1st. Yeah, it's March 1st already. And then I'll show you the answer. Let me go to edit. And here are the questions. Yep, that's right. The whole concept of doing taxes is actually foreign to a lot of people from other countries. Alright, so this is your row taking word. I'm going to copy and paste it so you won't type it wrong. The word is Kosh. Kosh is the name of a character from a science fiction show called Babylon 5. And the reason why I chose this name is because I think it was last week in this class, somebody said that the way I gave people answers is a little bit enigmatic. It could be my 440 class, I cannot remember which one, but the Kosh character in Babylon 5 is enigmatic. That's why I chose this name. There we go. Great sci-fi show in my opinion. But that's once again, outside of the scope of this class. All right, so I'm assuming most of you are done with that activity. Or did I release it? Maybe I forgot to release it. Sometimes I do that. I did not forget to release it, or I did. Oh, okay. I did forget. Okay. I did forget. Okay, the one thing that I was planning to do, getting there, I forgot. Well, I did disclose the answer, but I forgot to publish it. There we go. Now it is published. If you refresh now, you should see it. And while you guys are doing it, I'm gonna get some coffee. Now that was not enigmatic. That was just negligent. All right. So I am suspecting most people are done now. So we can continue with our little debugging session here. There we go. All right. So the syntax of accessing a member of a structure that is pointed to. Oh no 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 no. I have to redo the whole thing. It just timed out. Oh, it did not time out. Let's see. Did it? Which line am I on? Well, let's see. Can I still print PM? No, no, it lost it. Okay, now I have to run the program again. Alrighty. And I forgot to specify the whole thing. So let me run it again with dash n 1.234 E56. There we go. Wait, but let's not go yet, okay? So let's just look at this string here, okay? 1.234 E56. What does it mean? What is the value being represented? It is 1.234 times 10 to the power of 56. Okay, so keep that in mind. And now we are ready to move. Okay, now we are ready to kind of get back into the program, go back to the line where we stopped last time, and then we're gonna do a print, asterisk pn again, and then this time we look at the components where the coefficient is 1234, E10 is 53. So the question is, does 1.234 times 10 to the power of 56 equal to 1234 times 10 to the power of 53? Are those two numbers the same? Are they representing the same value? Exactly. Yep. So this is my way of um, getting around the problem of I'm not supposed to use a double precision floating point number ever in this entire program. Okay, because I'm now just saying, hey, I can play with the exponent of 10, then I can just use an integer to represent the coefficient. So I'm from the text channel, I think most of you are understanding that portion, and this is partially why you got the lab sessions that you got last week, is basically just to get you guys familiarized with exponents, logs, and stuff like that. Exactly, DIY double. Well, it's actually a little bit more than that because it is about the conversion of it's about a conversion. Okay, because I'm given a string that specifies a value as a base 10 scientific notation, and I want to convert it into a base 2 representation, a double precision floating point number representation. Now, there are certain things that are not illustrated here, like how do I do the base 10 conversion, because the coefficient itself is specified as a base 10 number. That portion, if you want to know, you can actually see it in one of the parse stuff here. So when you look at parse, it calls some of the subroutines. So we look at parse Mantissa. There's a little bit of stuff here that deals with the conversion, of a base 10 digit as a character in a string, and converting it into the value that we are trying to represent as a base 10 scientific notation. So, you can read the stuff here. I mean, it's all in here. I did not call some other subroutine to get this conversion done. All right. So now the question is, what about the syntax? How do we specify a component of a structure that is pointed to by a pointer? That's pretty easy. You actually get a choice here. Okay, don't you guys like choices? So one choice is to say, let's dereference pn first. So you get a structure. Once you have a structure, you can use the dot notation to specify which member of the structure that you want to access. So let's just say that I want to access the member called E10. So this is one way to access E10 as a member of the structure that pn is pointing to. Press the enter key, we get 53. Okay, that's cool. The other way is kind of more, it's more like a shorthand, and this is much more common in C and C++ programs, is to use dash equal to. It looks like a little arrow, so this is the shorthand because this notation here means exactly the same thing as the other one. It's just that the second one is more popular, and it's basically taught by textbooks and whatnot. But all it is a shorthand of the first one. You're basically dereferencing the pointer first, and then you're specifying which member of the structure that the pointer is pointing to that you want to access in that case. And this is it. Okay, this is struct and pointers in a nutshell. Any questions? Um, I think I did specify that earlier. See if you guys can remember. What does E2 represent? Remember the expression, the equation that I showed you earlier? V equals to blah 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 blah. It does mention E2. So what is the role of E2 in that equation? Nope. That is not what it is. It specifies a component of the value that we want to specify, and it is the power of 2. It is the exponent of 2. So this is telling me that not everybody is opening the lab, because if you had the lab right in front of you, you would know what E2 is doing here. That's what E2 is. That's what E2 is doing. So initially it is a 0, but eventually it is not going to be a 0. And I know I misspelled this. Okay, it's supposed to be coefficient, not coefficient. It's coefficient, not coefficient. So it's a typo. But I can't fix the typo now that you guys have opened the it's classified as a quiz, but it's not. It's really just an assignment. All right. So does that answer the question of what E2 and E10 and coefficient are doing in terms of the specification of the value that is being represented? Oh. I'm not getting an answer. All right, so let me repeat the question. Are we okay in terms of what E2, E10, and coefficient are doing in terms of how we are representing a specific value? All right, cool. All right, excellent. The input was 1.234E56 in the debugger. Oh, I better get back to the debugger and make sure that it doesn't time out if it hasn't timed out yet. Oh, there we go. Oof. Okay, because otherwise, it's going to time out. But I'm really done here. I mean, this is what you're given with. Okay, so the question is, what are you going to do with this, structure here? Okay, so let me get back to the entire PN. So I want you to preserve V. And obviously, someone's going to say, what V are we talking about? Yeah, that V that we have been looking at here. Okay, so this V. So I want to preserve this V as much as I can. I am free to change the other three components. Okay, so I'm free to change the coefficient. I'm free to change E2. I'm free to change E10 as well. So having that flexibility to change coefficient, E2 and E10, I want to conserve and I want to keep representing the same V. Okay, so you go like, oh, that's pretty easy. You can always just kind of do something with coefficient and then change increment or decrement E2 and then increment or decrement E10. Yes, so that's kind of the idea. However, the restriction is specified. Where is it here? There we go. So the restriction is specified here. When your algorithm is done, when that subroutine is done, I want E10 to be 0. Alright, so E10 needs to be 0. E2 has no specific restriction. It can be any integer, can be because it's signed, so it can be positive or negative. Okay. Coefficient also has its own restriction. Coefficient needs to be a true 64-bit integer, which means bit 63 needs to be a 1. Okay, so that's one restriction as well. So you have all of these restrictions, but we still want to preserve the value being represented. That is what your program, that's what the code that you are going to write is about to do. So do we have a question about the objective of the code that you are going to write? Not necessarily how to do it, just what it is supposed to do. All right, we got a few people typing in the text channel. So you can use the voice channel if you want to ask questions with your voice too. So the sign of the coefficient has to be 1. No, the sign doesn't have to change. Whatever sign it starts off with, you can keep it the same because that's not important to us. The sign is going to be preserved, right? The V is not supposed to change, so it cannot go from positive to negative or negative to positive because we are supposed to preserve the value. So the sign doesn't really matter. All you should be changing just the coefficient E2 and E10. Alright, and then Mark said, so essentially we'll be turning a number formatted as coefficient times 10 to the power of exp 10. Yes, yes, exactly. In other words, through the code that you are going to write, E10 eventually will become 0, and then E2 will change to whatever is necessary, so that coefficient as a 64-bit unsigned integer times 2 to the power of whatever E2 is supposed to be will preserve the value of V as much as possible compared to the string that serves as the input to the program. Now, I can only say preserving the value as much as possible because it is not entirely possible to preserve the entire thing. So it's not going to be 100%, but it should be as close as possible. All right, so and Igor is also typing, and we'll see what question is there. And I'm just looking at the time. We still got plenty of time, so I think we're good. Well, it's not a log conversion per se. It is. You can. It does have some component of log in it, but it's not going to be using the math log. So I'm going to show you guys exactly how to do it. All right, so we don't have any questions. All right, so let's get back to the module because the answer is there already. Some of you, might have read ahead of time, and you go like, oh, okay, I know exactly what to do, in this case. So we are skipping to section 5.1. Doesn't mean the other ones are not useful, but because section 5, okay, if you look at the text in section 5, that's exactly what your program is going to do. Your program is going to preserve the sign, so the sign does not change, but it is going to use a different coefficient compared to what it started off with, because the idea is we want to get rid of E10 and we want to use a non-zero E2 combined with some kind of mantissa M2 to express exactly the same value as the one that was specified as a base 10 scientific notation. So let's go ahead and see how we can do that. And we're going to do it in steps, okay? All right, so there are 5.1 is done already, okay? Getting rid of the decimal point of the mantissa, done. That's why we went from 1.234 to 1,234, and then we just kind of adjust the exponent of 10 to compensate for moving the decimal point 3 places to the right hand side for the mantissa. So that part is basically 5.1. So 5.2 has 2 subsections. One subsection has to do with a negative exponent, exponent of 10 being less than 0. That's your homework, okay? So your homework has to do with section 5.2.1. At least this one, the next one is going to be the other one, okay? But for this one, it is section 5.2.1, which means if you're taking notes, you should be. You might want to write down section 5.2.1, okay? That's where the theoretical discussion is, okay? All right, so now we're going to talk about how do we do this conversion, okay, and how do we preserve the value as much as we can, okay, because that's going to be the challenge, okay, is to preserve the value as much as we can. Now this is a different tab, so don't worry, we haven't lost the other one, even though it might have timed out. Yes, it timed out. That's okay, not a problem, okay, because now we can actually time out all we want, and it's not going to be a problem. All right, so I'm going to illustrate a few things first, okay? Because you're not supposed to use float. You're not supposed to use double, not typecasting, not using the variables, not using those types at all. Okay, if I see a double, if I see a float, if I see any references to those things, or anything that is coming from math.h, you're not meeting the requirements of the assignment. Okay, so we can only rely on integer stuff, right? So if you can only rely on integer stuff, we're going to have a few problems, okay? But we have solutions to each of those problems. The first one is precision. In other words, if I'm supposed to, okay, let me, let's see what would be the best way to do this. I can just use the debugger to do it. So let's go ahead and debug this program again. So run -n 1.234 E56. There we go. All right. So we're at the same breakpoint, and if we look at whatever is in Pn, it is like this. Okay. So one thing you can say is, hey, if we just need to get E10 to 0, okay, let me run this one more time, because we are supposed to deal with a negative exponent. This is a positive, this is a non-negative exponent of 10. So we'll change it a little bit, right? So we have 1.234. Let's try a negative just to make sure that the sign is working too. So negative 1.234 E negative 56. There we go. And now we print star Pn. And it has a sign of 1. Okay, that's what it's supposed to be, because sign is 1 means the number is negative. And we have the same coefficient because that's what we want to do. We want to use an integer to represent the coefficient part. E10 this time is negative 59 instead of negative 56 because every time we shift the decimal point for the coefficient, we are multiplying the coefficient by 10. So somebody has to compensate for the extra 10x, and that's done by decrementing E10 by 1 every time we do a right shift with the coefficient. So now we have a E10 of negative 59. All right. So first question is, how do we get rid of E10? How do we make it 0? So you can say, well, we can just increment it, right? We can increment it from negative 59 to negative 58 and so on and so forth. Okay, so how do we do that? Let's see, what am I gonna do here? Because I want to show you the math, but I don't want to use the debugger for that. So I'm gonna use a different window to show the math itself. Let's see. This is pretty simple stuff. I don't need to use math equations, so I'm not going to use Markdown. So I'm going to use my just plain text editor here called Mousepad. All right, so open it all the way over here, and then I can just drag it back here and get rid of line numbers because we don't need to look at line numbers. There we go. All right. So what we have here is the coefficient. I'm just going to abbreviate it to C in this case, times 2 to the power of E2 times 10 to the power of E10. Okay, so E2 is initially 0, and E10 is initially negative 59 in this case, and then C is initially 1234. So let me just kind of write it down. C is 1234, E2 is initially 0, and then E10 is initially negative 59. All right, so we want E10 to go from negative 59 to negative 58, right? So now we want to ask the question. V is still being the same value, which used to be 1234 times 2 to the power of E2, which is 0, right? And times 10 to the power of, in this specific case, negative 59. All right, so this is the value that we are trying to represent. So now I want to gradually change the power of 10 to 58, negative 58. There we go. So the question is, how do I do this? Can someone tell me what I can do to make this happen? What would be the most obvious way, the most intuitive way to make this happen? I'm incrementing the power of 10 by 1. What do I need to do to the coefficient in order to maintain the value being represented? Divided by 10. Very good. Okay, great. Okay, this is algebra stuff, right? Yeah, we just have to divide the mantissa or the coefficient by 10. Easy peasy. Okay, so we just have to keep doing this until E10 becomes 0, right? Because we can just keep incrementing it, keep dividing the coefficient by 10, and in no time we'll be done. What is the problem with this approach? We have a division by 10. So 1234 divided by 10 is not 123.4. Normalized or not is not a problem, okay? Because the homework assignment specifically want the coefficient to be exactly using all 64 bits of an unsigned 64-bit integer. So it's not going to be normalized to begin with, okay? So no worries about normalization here. We lose precision. Very good. Okay, because we have an integer division here. Okay, so we are not getting 123.4. Okay. And then some people look at this and go like, but Tech, this is like a pretty small percentage of loss. It's not going to be a problem, right? Well, if you do this a few times, it's going to be a huge problem because the number, the coefficient is only going to get smaller and smaller. And as a smaller value, you divide it by 10, the precision, the loss of precision is going to be getting worse and worse and worse. So if you compare 123 versus 123.4, it is approximately a what, 0.35 here percent of of error, it's still pretty bad, right? So, that doesn't seem like a very good idea. Okay, so how do we still need a division by 10? Okay, that is the only way to make up for incrementing the power of 10. So we still need that division of by 10. But what can we do to minimize the loss of precision? No, nope, that's not going to do it. We're losing the 0.4. Okay, so right now we are using. Nope, you cannot use double because that's the whole point of this exercise, right? You cannot use double. Well, how about this? How about I try to do this, but this time I'm going to do something else first before the division by 10. According to the notes, multiplying by 2, decrement E2 until we can no longer do that, right? We are basically saying, let's make that coefficient as big as possible before we actually do the division. So, the idea is this, okay? So let me just illustrate the actual number because this way you can actually see it, right? So instead of doing this, I'm gonna go like, let's multiply 1,234 by 2 first. So it becomes okay. I'm just gonna write it out, okay? So I'm gonna double that, and then you go like, but that's gonna change v. That's okay, because I can always compensate, right? Aha. Right? So now, instead of dividing 1,234 by 10, I'm now dividing 2,468 by 10. And the percentage of loss in this case is actually the same, okay? But I can do this again, right? So I can do this again. So I have 1,234 times 2 times 2 times power 2 minus 2 this time times power 10 negative 59. And this time it's going to be better because this time I'm actually increasing the number of digits in base 10 by at least 1, which means the precision is going to be a little bit better. Okay, so as you can see, I can do this as many times as I need until the coefficient can no longer that's the maxed out coefficient. So now the question is, what am I going to do here? What is this question mark here? Times 2 to the power of negative something times the power of 10 negative 59. In other words, I want this to maximize. But how? Okay, so I'm going to be more specific here. Okay, this is going to be maximized to the large to fit, but still fit. Okay, maximize but still fit in a unsigned 64-bit integer. But how do we do that? Okay, now you might recall that one of your labs actually has a math problem to solve like this. Okay, the one that has like we want x to be greater than or equal to 2 to the power of 52, but we want it to be less than 2 to the power of 53. Yeah, so we're trying to do that, but without using log. So instead of using log, you can use a loop. So what are we going to do? Well, this is coefficient. It starts off as 1,234. So we now say, and okay, so I'm going to also keep track of E2. Initially it was 0, right? So now I can say, let's double C, okay? It becomes 2,468, and then E2 becomes negative 1, and then C becomes twice of that. Yes, my arithmetic is not going to be that good, so I'm cheating on the side here, and just copy and paste 4,936, and then E2 is going to be negative 2. And then we double that again. I mean, obviously, at some point, this is just going to be silly because, where. So, but the question is, how do you end? Okay, Now, it looks silly, but it's not, okay? Because this is how you can identify what kind of control structure you will need, and also what to do to determine when you can the other things that you need to do with that control structure, okay? So the next one up, obviously, is going to be just that number times 2 again, which is 19,744, and then E2 is going to be -4 here. So as long as I make these adjustments, the V, the value being represented, actually has not changed. It maintains exactly the same. So the question is, how far can I do this until I say, oh, this is the last one, okay? Because if we double again, it's not going to be representable in as a 64-bit unsigned integer, okay? The question is, how do you determine that, okay? How do we know C is the largest value? Because if we double it again, it will no longer be within the range of a 64-bit unsigned integer. All right. Nope, you cannot log it, right? Because log is double. It's from math.h. If you touch log, you're going to lose points big time. So here's the all right. So from the questions, I'm going to say a lot of people did not read ahead of time, because if they did, there won't be any questions, which is okay, because otherwise I won't have a job either, because you guys can learn everything from just my text, which eventually you will need to do, because when you go to work, it's a different story, right? When you go to work, you're not gonna say, but boss, you have not taught me how to do this. That's not gonna work. All right, but since this is not work, this is a class, okay? I'm gonna show you how we can do this, okay? So now we're gonna say, okay, can we do this comparison? Can we just say that if C times 2 is greater than or equal to the maximum unsigned integer 64-bit number? This is not the right constant to use, but I'm just using it as a stand-in right now, okay? If this is this, then stop doubling, okay? The question is this code going to work? Obviously not, right? Because if it did work, why would I ask that question? I mean, you guys should know me by now that I'm not gonna ask a question if it's gonna work. Nope, it's not gonna work. The question is, why is it not gonna work? It really has to do with types. So this is back to the CISP310 concepts. It's not about assembly language programming or how we represent values. This is a C concept. Because what exactly is this constant doing here? What is it representing? It is representing the maximum value that a 64-bit unsigned integer can represent, right? If I can specify a value that is greater than that, that means this is no longer the maximum value that a 64-bit unsigned integer can represent. Are you guys getting this? How, if this is doable, then we have a contradiction. This term is no longer the largest integer that you can represent using 64 bits, because I have just specified a value that is greater than that, potentially. So it's not going to work. What are we going to do with this, right? But there's a way to do it. It's called algebra. Exactly. So Tam is right. It's called algebra. Let's divide both sides by 2, because the order or the comparison would actually be preserved, right? Except now we can actually do it, because now we are basically saying, if you want to know if doubling is going to be too much, then you can ask, is it now already exceeding 1/2 of the largest integer that you can represent in 64-bit. Because if it is already greater than 1/2 of that value, then don't double it, because we are done here. If you double it, it's going to exceed what we can represent using a 64-bit unsigned integer. Is that logic working? Is that math working? Remember, computer science is a branch of mathematics. But is it working? Are you guys kind of grasping that idea? Maybe, maybe not. Okay, excellent. Okay, that's good to know. It's comforting to know. All right. Okay, so now my job is to say, well, I said earlier and said that this is just a little placeholder because I'm not remembering, whether that's the actual name or not. So the way you look it up is to look up the header file that I used to refer to the type uint64_t, and it is uint standard integer.h. This is the header file. So that's going to be your first clue, is to say stdint is a header file, and you want to find out how to specify the maximum value of 64-bit integer. You guys cannot see what I'm searching, but it's going to be pretty clear what I'm typing. And Google is good, but not good enough. It's good, but not good enough, because it does show you the actual value here. But if you just kind of copy and paste it, it's not going to work because it has got all the commas, right? So you can say, well, but I can just copy, paste it, and then remove all the commas. Yeah, that's going to work. However, that's not really the best way to do it. So you want to look into, this is one resource. The better resource to look for this is here. That may work. Okay, there's a CPP reference, which is here. There we go. All right, so this is fixed with integer types. It gives you, all of this stuff here. So we are looking for uint64_t, which is a 64-bit unsigned integer. And we don't need to know the width. We want to find the maximum, right? So there we go. Unsigned integers, maximum value. And, for a uint64_t, it's going to be one of these 4 things here. I'm not going to tell you the answer. Okay, I'm not going to give you the answer to this one. Okay, you guys will have to figure it out. Okay, but it's one of these 4. One of these 4 constants will specify the maximum value of a uint64 unsigned integer 64-bit number. Yes, Taylor is probably on the right track. Yep. Oh, but it's not 8, right? It's 64. What about just taking this number here and just multiply by 8? That should be the answer. That should be the same as taking the second one and multiply by what, 4, or taking this third one and multiplying by 2, and the same as the fourth one over here. So just to be fair, I'm gonna say I was just kidding, okay? Because I don't want someone to tell the dean of BCS and go like, Tech gave us wrong information. But then he said it is wrong. So I didn't actually give you wrong information, because if I gave you wrong information and did not tell you it was wrong, that would be wrong. But if I tell you wrong information and then tell you it is wrong, it is right. 2 wrongs make a right. The negation of a negation of something is the non-negative version of that something. Yeah. Yeah. All right. That I do not know. I think FAST64, that I do not know. I have to look that up. Okay, so we got some stuff figured out already. Okay. So now we're going to look at this and go like, okay, now we know when to stop doing this, right? So if you guys want to know, how far this is going to have to go to before we can stop, let's see, what would be the best way to do it? Do I have time to do it? I may not have time to do it, but you guys get the idea, right? So let's just say that at some point, I mean, you can actually figure out, how many times we have to shift this, or multiply by 2 before it runs out. Okay, so let me see. I'm just going to use a spreadsheet to cheat here because I do want to give you a practical value, just so that it's correct. So we're going to use this guy here. It's a spreadsheet. Um, and no, your C program cannot, shout out to a spreadsheet to do the calculation. Just in case somebody is thinking this, oh, this is a great idea, I can do this. I can just shout out from my C program to a spreadsheet, have the spreadsheet to do all the calculations, and then we'll grab the result of that, and then put it back into the program. Nope, that's not what I want you guys to do. All right, so on this side, I'm going to specify a comparison because I want to see if this value is greater than or equal to 2 to the power of 64, the whole thing minus 1. Now, obviously, that minus 1 is not going to be making too much of a difference. And I know some of you are probably thinking, but Tech, you just said this is not going to work. It's not going to work if you are restricted to using uint64_t, but the spreadsheet is not, does not have that restriction. So that's why it's going to work here. But I'm only doing this to illustrate that at some point it's going to exceed it, right? So this is the last value that we can actually use. That I'm not sure whether you guys can see or not, but there we go. Okay, so this is the last value that we can use because it is, if we double it again, it's going to exceed what a 64-bit unsigned integer can represent. All right. So we're going to take this number, which is basically 1.11149 and then times 10 to the power of 19 something. So we're going to take that and go like, then what do we do with it, right? Okay, so we'll go ahead and punch that number in, and looks like it is it's 54 times. Okay, so I'm just going to do this on the side. And 2 to the power of, okay, 1 is 0, so 53. Yep, I got it. Because I have the exact number, because I'm going to paste the exact number. Oh, that's not it. That is not it. Okay, try it one more time. Okay. Control Shift C for copy, and then Control V for paste. There we go. So this is what C is supposed to end up at. And then E2, let's see, we're going to have to do it, let me see here, 53 times. So it's going to be negative 53. All right. And all this time, right? All this time, what is E10? E10 has never changed, okay? Because I've just been messing around with the coefficient by doubling it. So the only thing that got changed, is the E2. So E10 has not changed. E10 is still going to be the same as what it used to be, which was negative 59. All right. So now I know the coefficient can no longer double. This is all I can do with given a 64-bit unsigned integer. What am I going to do now? The one thing that I wanted to do to begin with, but then I didn't want to do it because I would have lost a lot of precision. Divided by 10. Christopher is right. Okay, now we can divide it by 10 finally, right? So if you divide this by 10, okay, so I'm gonna show you what happens when we divide it by 10. You guys go like, but Tack, we know what's gonna happen if we divide it by 10. We lost this 8, right? Yes, you're correct. But don't you think this is not right? Because it looks like every time we divide it by 10, because it's an integer division, the result is always smaller than what it's supposed to be. That's a bias, okay? It is a bias, not in the cultural sense, but it's a bias that every single time we perform an operation, the error is always going in one direction, which is not good, okay? So how do we fix that problem? Because this is the same thing as taking the floor of something always, and it's causing a problem because it is always going to be smaller than what it's supposed to be. So what is the other way to do something like, okay, I know the result is not an integer, but I want the result to be as close as possible to what it's supposed to be instead of always taking the floor of that. One of your labs, introduced this concept. And what exactly is it again? Rounded. Exactly. Okay, very good. So both Hong Hu and Bernard are correct, and Philip as well. So the add 5 is to do it before the division. Okay, because this is what we found, this is what we learned from one of the labs. If you take the round of x divided by 10, it's going to be the same as the floor of x plus 5, which is 10 divided by 2, the whole thing divided by 10. All right? That is why the lab had that question. Okay, and it introduced the concept of how we can do rounding, but without using double, right? This is all integer math. So that means in order to do this, I'm going to have to add 5 to this first. Okay, so the actual calculation is going to be plus 5 first before we perform the division. So this does, kind of throw a wrench into how we check whether it's time to get out of the loop or not, because we have to eventually add this 5. So that means we kind of have to make sure that adding this 5 is not going to overflow or exceed the range of a 64-bit unsigned integer. Minor detail, but nonetheless still important. So if you do this, this is the rounding. Now we get closer to what it is supposed to be. And even though this is still an error, sometimes it's going to be a little more than what it's supposed to be, and other times it's going to be a little less than what it's supposed to be. So that is good, right? Because now we are not erring only in one direction. Now we are erring in both directions, and hopefully over time it's going to average out, and the end result is going to be as precise as we can get. Okay. All right. So what are we going to do with this? Are we done yet? Well, not quite, right? Because now we have just, we have one single division by 10, which means E10 can now get one step closer to 0. Wow, great. Okay, so then what are we going to do? We do this all over again, right? We look at this number here and say, is this as big as we can get, to before we can divide it by 10 again? The answer is obviously no, because this, darn it, an error. Okay, because this was the largest integer that we can represent in 64-bit before it exceeds the range. And we have just basically divided by 10. The rounding part does a little bit of something to it, for rounding, but for the most part, we have just divided this number by 10, which means we should be able to multiply this value, this one here, by 8 and not exceed, because 8 is less than 10, right? Sometimes you can multiply by 16, other times you can only multiply by 8. But why do I want to, kind of make that differentiation, right? Because I can now just say, hey, we can now say this number and then multiply by 2. So I'm going to do this on the side just so that all right. That's not working. All right, let me try that one more time. Control Shift C, Control Shift V here. There we go. All right, so I can show you what I'm actually doing on the side, because otherwise you guys will be bored. All right, so I'm just using a calculator, line calculator, to do exactly the math that we were doing. So add 5 to it, divide it by 10. And it did not like it because I was supposed to do a /10, not a question mark 10. There we go. It still doesn't like it because I forgot a close parenthesis. There we go. Alright, so now we take this value and then we ask, let's go ahead and multiply by 2, see what happens, right? So, alright, so we take this value, multiply by 2. That's not exceeding the range yet, so we'll multiply that again. So basically, in the end, we are multiplying by 2 by 2 by 2, And we look at this value and say, if we double this again, is it going to exceed the range of a 64-bit number? The answer is I really don't know, okay? Because now I have to just really say what is 2 to the power of 64 minus 1, and that is the value. So we are getting pretty close, and I think I'm gonna say if we double again, it's gonna exceed the range. So eventually, okay, you guys have to decide how to determine when to stop. But eventually, this c, the coefficient, is going to be this number, which is the last value before you run out of space in the 64-bit integer. So now that c is this value, e2 is going to be because we did 3 multiplication by 2, so that means e2 is going to be negative 56 now. E10 is going to be the same because we didn't do anything with 10. So now we are ready for another division. Oh, never mind. There we go. So now we are ready for another division. So the other division by 10 is going to take this value here, and what we're going to, oops, no, okay, there we go. So we're going to add 5 to this, okay? So we can put an open paren here, and then we divide it by 10, and that's going to be some value, whatever value it is, it becomes the new value of c. E2 is maintaining because this division by 10 has nothing to do with base 2, but E10 on the other hand can increment again, so it becomes negative 57. So are we doing okay so far with the logic of this code? Obviously, I'm not showing you the control structure to get this done, but I'm showing you if you were to do it by hand, this is how you do it. Okay, so you keep doing this until E10 increments to 0, then you're almost done because we have to make sure that C is the largest value before you run out of space. So you have a little bit more things to do, by the time this code exit loop, but not a whole lot. So I'm gonna ask. I'll see if you guys have any questions. It's 6:52 right now, but since the lab is not due at 9:50, I'm gonna, just kind of exceed the lecture time just a little bit. So this way, you guys will have a better starting point in order to get your code in. So if you have any questions, go ahead and put it into the text channel. And if not, I am going to go back to the equation earlier because I want to determine, when can we get out, okay? So I'm going to work out some math here. Because this seems like an important comparison, okay? If C is greater than or equal to the maximum value of a uint 64-bit number divided by 2. This seems like a very important condition, but there's a little bit more to it, right? Because we also want to make sure that if we add 5 to this C, it's also not going to exceed what a 64-bit unsigned integer can represent. So the question is, we know that we have to kind of subtract 5 somewhere. The question is, are we going to subtract 5 before we divide it by 2, or are we going to subtract 5 after we divide it by 2? So this is one option, and this is the other option. Only one of them is mathematically correct. The question is, which one is correct? So this is once again algebra. All right. The second one. All right, so let's see whether it is the second one or not. So if you're going for the second one, and C turns out not to be greater than or equal to this value, then you're going to double it again, and then it's let's just say that when you double again, it is no longer less than this value. It is now greater than or equal to this value. So the problem is, if C is greater than or equal to this value, and then you add 5 to it, there's always room I think we can go for the first one. Let's see. Let me double check. So if C is greater than if C is still less than this amount, we can double again. And when we double again, it is guaranteed to be less than or equal to this amount, which means we still have room for the plus 5 before we run out of the range of the value. So I think it is the first one, not the second one. My notes may not be right, by the way, because I think when I typed this, I might have worked out the algebra part incorrectly. Let me see. Yep, so the notes is actually wrong because it's supposed to be the largest possible numerator divided by 2 and then do the subtraction by 5. Let me think about this one more time. All right, one more time. All right, so if C is greater than or equal to this amount, then we know for sure there's room to add 5. If it is greater than or equal to this amount, we are not so sure because it is okay. So that's right. Okay, so if C is already greater than or equal to this amount, if it is just less than and we double it, no, I think this is right. Okay, the second one is correct. Do the minus 5 outside after the division by 2. Yeah, you can do the minus 10 over here. I mean, you can do your algebra thing. Just you put this over here. You can say this number minus 10, and then the whole thing divided by 2. That works too. Yep, because it's the same thing, right? Because if you take this out, then you have just that. So both method works, but I think the first one does not work. The first one is the one that is mentioned in the notes, I think. Let me double check. Because we want to do the subtraction of 5 out after the division. And the note says largest numerator. Yeah, so the note is wrong because it's doing the minus 5 before the division by 2. We should do the minus 5 after the division by 2. So I'll go ahead and fix that, but that's the last little piece of thing that we need to work out is when do we do the subtraction of 5? And I think the subtraction of 5 is after the division by 2. Christopher is actually correct. Okay, yes. So it is the subtraction of 5 divided by 2. So my note is right. Okay. I am convinced. Because if it's less than, okay, so if it's less than, then we double again, and after we double again, it would still be, it would still have the room of 5 left. Okay, yep, okay. So I am convinced. All right, so sorry about the confusion. So the Christopher's answer is correct. So is what is written in the notes. That's it. All right, any other questions? Let me kind of go back and correct myself in the notes that I captured today. So this way we know which one is right. So we want to do the subtraction of 5 before we divide it by 2. So this is the exit condition. Or, stop doubling. There we go. Any questions before we end today's lecture so that you guys can get started with the homework? No further questions. All right. Well, if there are no other questions, I'm going to stop the screen share and also YouTube. Um, but I'll still be online. Okay. If you guys are going to be working on this program, I'll be online in case you have any questions, especially about pointers and structures, because you got to have that done. Um, so the lab on Thursday is going to be, you're going to have two assignments and they're going to overlap a little bit. I haven't really quite decided on whether to assign the other one on Thursday or not. Um, if not, then we're going to use the lab time on Thursday also to kind of work on this program. And because this is actually just a program, unless you have a concept question, you might want to just use direct message to contact me, because I don't want partial answers to be disclosed through the text channel. But if you have a concept question, you can post it in the usual text channel for the day, because that's just a concept thing, and other people may have the same question. All right. Any questions before we stop the screen share and the live stream? All right. Doesn't look like there are any questions. And I'm going to work on the code to generate the key for the exam. So this way, even if I may not be able to grade it anytime soon, or finish grading anytime soon, you guys would know the answer to the questions. Yeah, so I can do that. All right, looks like people are dropping off, so I'm gonna drop off as well. But I will still be online if you have any questions related to the discussion tonight, or if you have any questions about exam one, I can explain some of the questions or explain the answer. All right, so that's it, and I will let you guys go.